Hello and welcome to this first video on vectors. So there are basically two types of physical quantities, namely vectors and scalars. So what is a vector? A vector is a quantity that can be described by both magnitude and direction. Example: force, velocity, acceleration, etc. Now it is very easy to view force or to see force as a vector. For instance, if we have a block of a certain mass, we don't know what the mass is, and we intend to move this block from this point x to say the point y. In that case, there must be an external force that will be applied to the block, so that if the force F is applied to the block will move and change its position from x to a new position y. Now, this block is expected to move in the direction of the force applied. So what happens here? A certain force is applied which can be measured in newtons. For example, say 20 newtons of force is applied, and the block changes direction from where it was to point y. So by virtue of the force which has been applied to the block has changed its position, and therefore its direction has been changed from point x to point y. So the block will move in this direction. So force now becomes a vector quantity in the sense that we can measure how much force has been applied, for example 20 newton of force, and we can also see that the block has changed its direction from one place to the other. So we call force a vector quantity. And there are other vector quantities like velocity is also a vector quantity, acceleration, etc. Like for velocity, if a driver moves at say 20 meters per second from say a town, Calabar, to another town, Ecom, then we see that velocity here is a vector, in the sense that we can measure how much the velocity is 20 meters per second, that is the magnitude or the size, and then we can also see that the driver had moved in a specific direction from Calabar to Ecom. So we are able to specify the direction of the driver, and we're also able to specify how much the velocity of the driver was. So 20 meters per second is what we refer to as the magnitude here, or size, and the fact that the driver moved from Calabar to Ecom specifies the direction. So in this sense, velocity here becomes a vector quantity. On the other hand, a scalar is a quantity that can be described by magnitude only. Example, we have mass, time, temperature, and so many other quantities. Now when we go to scalar, let us pick up mass, for example. Now back to this, our example of a block. Now if a block, like we said here, has a mass of 50 kg, so a 50 kg block, 50 kg here simply means the size of the block, or what they call the magnitude of the block. So if a block is 50 kg, that is all about the block. So here mass is just a quantity that has no direction. Another one here is say temperature and time. If the temperature of your body is 35 degrees Celsius, it doesn't make any sense saying 35 degrees Celsius north or 35 degrees Celsius east or west. It doesn't make any sense to say that. So such quantities are called scalar quantities. How about time? If the time is 2 o'clock or 12 noon, you can't be saying 12 noon north or 12 noon south. So such quantities are what we refer to as scalar quantities. So in this course, our interest will be focused on vectors, that is quantities that can be described by magnitude, both by magnitude and direction. Geometrical representation of vectors. Now, geometrically, we represent a vector by an arrow like this, an arrow. And on this arrow, we can just call this vector, say A. So notation. So here I have called this arrow a vector A. So I have written A, letter A, with an arrow over it, and that means vector A. You can also write, A with just a bar on top of it. That also means vector A. Then other times in print, we could just write a bold-faced letter A. So any of these represents a vector A. So A with an arrowhead, A with a bar on it, or just a bold-faced A. So in most printed materials, what you see is a bold-faced A. But throughout this series of lectures, I'll be consistent with I'll be moving between the A with the arrow and A with just a bar. So whichever one you come across, in the course of this lecture, would still mean a vector. So with this, I can call this arrow vector A. You can call it another vector. You can say vector B or vector C, whatever it is you want to call it. But what we see here is that this arrow, which I have called vector A, has a point here, 0, which is called the initial point or starting point. And of course, at this point here where the arrowhead ends up, we call this point, let us call that point P, and point P here is called the terminal, or in other terms we can call it the terminus. So this arrow here represents a vector A with initial point at O and terminal point at P, or with starting point at O and the terminus at point P. Now, we said that the vector is a quantity that has both magnitude and direction. It is obvious from here that the arrowhead here tells us the direction of this vector. So how about the magnitude? Now you see that this vector here, what we now call vector A, has a length. So the length of this arrow is what gives us the magnitude of the vector or the size of the vector. So this is the vector A. Now the size of this vector or the length of the vector is represented as A between two straight bars. And we will call this the magnitude of vector A, or what we call the modulus of vector A. So this is the magnitude of vector A, or the modulus of vector A. So vector A is a vector that begins from point O, or that starts from point O and terminates at point P. And the length of this vector A is represented as A between two straight lines. So going forward, whenever we see a vector written between two straight lines here, this simply represents the length of the vector, or the magnitude of the vector, or the size of the vector, and in other words, you can call it the modulus of the vector. Let's look at a few types of vectors. Number 1, the zero or null vector. A vector whose initial and terminal points coincide is called a zero or null vector, and is denoted as a 0 with an arrowhead on it. So if I have this as a point, and I claim that this point is a vector, and I call this point, say point O, then it's obvious that on this point, the initial or starting point coincides with the terminal point. So if this vector O here will be nothing but the 0 vector, because the starting point and initial point both coincide. And of course, for a 0 vector, the length of the 0 vector is 0. Hence the 0 vector. And of course, in terms of direction, the 0 vector points in any direction. So if you claim that it points to the north, is to the north. If you claim it points to the south, there's no issue. So 0 vector is simply a vector whose initial and terminal point coincide. And how do you know them? You simply see us write 0 with the arrow on top of it. So that means that vector O is a 0 vector. And the beauty of it is that whenever you add the 0 vector to any other vector, say vector A, that is not a 0 vector, we always have vector A. So if we add a 0 vector to another vector B, we always have vector B. If we add the 0 vector to a vector C, you always come up with vector C. So in this sense, the 0 vector is simply acting like what? Like the identity element, or the identity vector of all vectors. Equal vectors. Two vectors, A and B, are said to be equal if they have the same magnitude or size and direction, of course, regardless of the initial point. And we'll write that vector A is equal to vector B. So if we have a vector A, and we have another vector B. Now, if the magnitude or the length of vector A is the same as the length of vector B, first condition. Second condition is that if vector A and B are both pointing to the same direction, for example, if vector A is pointing to the direction, let's say northeast, and vector B is also pointing northeast, then we say that vector A and vector B are equal vectors, or we say that the same vectors. So vector A and vector B are called equal or the same vectors if two things happen. One, both vectors have equal magnitude or equal length, and two, both vectors are pointing or have the same direction. Like we said, regardless of the initial point. You can see the initial point of two vectors are different. Vector, this is OP, this is let's say AB. Of course, the initial points could also coincide, and there's no issue. So the only condition we require here for the two vectors to be equal is that they must have equal length or magnitude, and they must be in the same direction. Negative of a vector. The negative of a vector A is another vector of length A with opposite direction denoted as minus vector A. So if we have a vector, say A, and we have another vector that has the same size as vector A, so vector A has the same size as vector A, so let us call this vector, but opposite direction as that of A. So this vector will be called vector A, but now we say minus. So the minus here simply means that this other vector is in the opposite direction as that of vector A. And we'll call this vector the negative of vector A. And of course, vector A is also the negative of vector minus A. So negative vector, the negative of a vector is simply if that same vector with the same length, but with the opposite direction. So vector A and vector A, the length of this vector and the length of the second vector minus this are the same. The only difference is that the negative of vector A is in the exact opposite direction as that of A. So if A is in the north direction, then its negative will be in the south direction, which is directly opposite. If vector A is in the east direction, then vector A minus A will be in the west direction. So these are called negative vectors, and of course these vectors are negative of each other. Co-initial vectors. These are vectors that have same initial point, or these are vectors that have same starting point. Now if I have a point here, point O for example, and from this point I have a vector, say A. From the same point I have another vector, say B. I have another vector, say vector C. Then vector A, B, and C are said to be co-initial vectors because the vector A, B, and C all originate or all start from point what? Point O. So if I call this OA, call this OB, call this OC, what do you observe? You know that the starting point of vector A is O, that of vector B is O, and vector C is also O. So vector A, B, and C are called co-initial vectors. Co-terminus vectors. These are vectors having the same terminal point. For instance, if I have a vector, say vector A, I have another vector, vector B, I have another vector, vector C, I have another vector, say vector D, and one last vector, say vector E. What do we observe from these five vectors? These five vectors all have different initial points, but the same terminal point. So when vectors have the same terminal point, they are said to be co-terminus. And like in the previous example, when they have the same initial point, they are said to be co-initial vectors. Parallel vectors. Two vectors are parallel if they have the same direction or are in exact opposite directions. Have to be very careful here. Let's look at this. For instance, If it's a vector, say vector A, another vector, say vector B. Okay, now if vector A and vector B are in exact same direction, then vector A and B are said to be parallel vectors. And on the other hand, if this is vector A and vector B is in the opposite direction, in the exact opposite direction as vector A, then vector A and B again are said to be parallel vectors. You observe here that in the definition of parallel vectors, we have not said here that we have not said anything about the magnitude or the length of the vectors. So vectors are parallel irrespective, okay, of their length. So it is possible that vector A is a longer vector than B. It's also possible that vector B is a longer vector, than vector A. It's not important. What matters is that if vector A and B are parallel vectors, then they must either be in the same direction or they must be in the exact opposite direction. And we can have more than two vectors. So if this is vector A, another vector, say vector B, another vector, vector C, another vector, say vector D. If these four vectors, in fact another vector this way, say vector E, say vector F again. So vector A, B, C, D, E, F. And so if these vectors, alright, are all in either the same direction or in the exact opposite direction, then these vectors all will be called what? Parallel vectors. Now one thing we must observe about parallel vectors is that, let us take these two for example, vector A and vector B. And you'll observe that vector B is some scalar multiple of vector A. You observe that if we put vector A, let's for example twice, we'll get the length of vector B. Do you observe that? So for parallel vectors, this will always be true. Okay, that when two vectors are parallel, it is possible that one of the vectors is a scalar multiple of the other vector. We shall look more into this in later videos. Collinear vectors. Now, if we have a straight line and we have 3 points on that straight line, say point A, point B, and point C, then if these 3 points, 1, A, B, and C, are on the same straight line, then we say that point A, point B, and point C are collinear points, right? Or are collinear. Now, the same idea extends to vectors. Now, if for example we have from A to B, we have a vector. The initial point is A and terminal point is B. And from B to C, we have another vector. Well, have another vector. It would have been this other way. Point A, point B, and point C. Point A to B, we have a vector in this direction. And from point B, let's say from C to B, we have another vector that is opposite to vector AB. Now, these vectors, AB and BC, let us name them. Let us call the vector AB, call it vector A. Vector B to C, let's call it vector D. Vector AB here again, call it vector A. Vector C to B, let's call it vector E. Now, these two vectors, A and D, are collinear vectors. These two vectors again, A and E, are also collinear vectors. One thing we must observe here very strictly is this. Collinear vectors are also parallel vectors. We should take note of this. Collinear vectors are also parallel vectors. The difference here is that here we are saying that collinear vectors will lie on the same, same support or the same line, if you like. They are on the same support or line. But for parallel vectors, so parallel vectors could be on the same line or on different, lines. But the fact is that when they are on different lines, we ensure that they must be in the same direction or in the exact opposite direction. And if they are collinear, then they must be, on a line like this or on the same support. However, in both cases, whether they are collinear or parallel, both are still parallel. Therefore, the relationship we had for parallel vectors still applies to collinear vectors. So if two vectors or three vectors are collinear, it simply means that one vector can be written as what? As a scalar multiple of the other vector. And this is what we refer to as what? Linear dependence of vectors. Like I said, we shall look closely into these details in much later videos. So, clear distinction. Collinear vectors are parallel vectors. Parallel vectors are parallel vectors. But collinear vectors are special in the sense that we are saying that these two vectors lie on the same support or they are on the same line. Like vector A and B here are in the same direction. Vector A and E here are in exact opposite direction, just like we had for parallel lines. for parallel vectors, I beg your pardon. Free vectors. Now, if parallel displacement of a vector doesn't change its magnitude and direction, such a vector is called a free vector. For instance, if we have a vector here, vector A. If I move this vector to this other point, you observe that vector A, let me call this one now vector B. In fact, the same still vector A. You observe that vector A, if these two vectors have the same magnitude, the same length, and the exact same direction, even though they are different points in space, then this vector A is called a free vector. Okay. Now let's go back to these collinear vectors. You know, we can look at vector D as vector A that has shifted its position from here, its initial point from A to B. But what do you observe? Vector A here and vector D, you know, vector A here can be called a free vector in the sense that, okay, it has changed its displacement from here to this point, but its magnitude has not been changed, and likewise its direction. So if I have another vector here, say vector E, and I take this vector, I displace it and write something and draw another vector here. If this new vector is the same length as vector E and the same direction as vector E, then vector E has just been displaced. In that case, vector E is called a free vector. So by free vector, I can always move the vector from one point to the other. I can always move the vector from one point to the other on the condition that the vector remains the same in length and remains the same also in direction. Unit vector. This is a vector of length 1. So if I have a vector here, say vector A, and the magnitude or length of vector A is 1, then vector A is called a unit vector. Now this vector is very important in the theory of vectors. Now look at this, for instance. If I have a vector here, call it now vector C. Okay, it is possible to find the unit of this vector. Now it's obvious that this vector C is not a unit vector, since it looks as if the length of this vector is longer than 1. Okay, but we can get a unit vector of this vector C. Let's suppose that this is a vector of length 5, for example. I want to get a unit of it. What do? We divide 5 by 5, is it not so? And that becomes what? 1. And that's a unit of the vector. In the same sense, if this is vector C, okay, and we want to find the unit vector of vector C, that means we want to find a vector that has what? Length of 1, or that has a magnitude of 1. But take note, the unit vector of C, let me now call this vector. So I'll call it C hat or C circumflex. Now, the unit vector of vector C is called C hat or C circumflex. Will be a vector of length 1 and will be acting or will be in the same direction as vector C. In other words, so how do I get this vector? What I will do is I'll simply divide vector C by the length of vector C. So if you divide the vector by its length, what you get is a unit vector of that vector. So vector C over the length of vector C gives us vector C hat. So C hat means unit vector of vector C, which is equal to C divided by the length of vector C. So if we do this, if we divide a vector by its length, what we get is a unit vector of such a vector. So the point number 1, the unit vector of a vector, or lies in the same direction or is in the same direction as the vector itself. So when you do this to a vector, we have just found the unit vector of vector C, and this is a term we call normalizing of vectors. Normalizing of vectors. So what we have done to C here is that we have just normalized vector C. So like I said, let me repeat that we have a vector C and we're interested in finding a unit vector of vector C. That means vector C could be of length, whatever it is, but we want to just find a unit of it. So how do we get a unit of vector C? We divide vector C by its full length. Okay? And when we do that, we'll get a unit of it. Now the unit vector of vector C is denoted as C hat or C circumflex. So this is a special one for unit vectors. And the good thing here is that, or what you should take note of here, is that the unit vector of a vector and the vector itself are always in the same direction. We shall talk more about unit vectors in the next video. Addition of vectors. Now if we have a vector, say vector A, Another vector here, so vector B. Question is it possible to add vector A and vector B? Yes, it is. So we can just, this becomes vector A is vector and vector B is a free vector. So we can, we can displace vector B and bring it to join vector A so that its terminal, its starting point is at the tail of vector A, and that becomes, and that is vector B. Now please take note, this vector is the same as this vector, that is a free vector. So it has the same length and exactly the same direction. Okay, so if that is vector B, then vector A plus B will now be the vector whose initial point is at vector A and terminal point is at vector B. So this is vector A plus B. So vector A plus B is a vector whose initial point is at vector A and final point or terminal point is at vector B. We call this vector A plus B. And of course, this is what we call the triangle law or the rule triangle law of vector addition. Let me draw this again neatly. So I have here vector A, and then vector B will start at the terminal point of vector A, and then if this is vector A and vector B, so the sum of vector A and B is a third vector whose initial point is at vector A and final point is at vector B. So that is vector A plus B, triangle law of vector addition. There is a second type of addition which we call the parallelogram law of vector addition. So it states that if two vectors acting simultaneously at a point, so here's my point, call it point O, two vectors, this is vector A, and this is another vector here, call it vector B. So that if two vectors acting simultaneously at a point O here can be represented both in magnitude and direction, like I've done here, okay, by the adjacent sides of a parallelogram, this is parallelogram, drawn from a point O, from this point, then the resultant value is represented both in magnitude and direction by the diagonal of this parallelogram starting from point O. What are we saying here? This is a parallelogram, okay, whose adjacent sides have been formed by two vectors. This is vector A and vector B. And what do you observe from A and B? Vector A and B are co-initial vectors. That is to say that the two vectors start from the same point. So what we're saying is that if this forms the sides of a parallelogram, then the resultant of these two vectors, the sum of these two vectors, will now be a third vector, okay, who's from here, the point O, to this diagonal here. So this is vector A plus B. The key difference between this parallelogram law of addition and the triangle law of addition is that in the triangle law of addition, you see that vector B, or you see that the starting point of vector B is at the at the terminal of vector A. But in the parallelogram law of addition, both vectors A and B have same initial point, are co-initial vectors. You see that? Of course, a parallelogram is made up of two triangles. So if you separate into two triangles, what you have here is simply the triangle law in two places. If I separate this, I'll have something like this. Okay, let's see. Yes, this side here. So this is vector A. Of course, this is a replica of vector B. So this is vector B. So what do you see here? Same triangle law of vector addition. Okay, so of course the other side of the triangle is a mirror image of this one. So vectors are added in two ways, either using the triangle law of addition or the parallelogram law of vector addition. Subtraction of vectors. So we want to check if we can perform vector A minus vector B. But here, geometrically we look at it like this, as vector A plus the negative of vector B. So in space, it's like this. If we have a vector, say vector A here, okay, and we have vector B, say this way, so this is vector B. Now if we intend to, okay, let's add these two vectors up and see what happens. We can draw this again as, let me use another pen. We can draw this as vector A, okay, vector A. Now if we take the negative of vector B, what will it become? It will become vector B in the opposite direction, right? So that will become vector B in the opposite direction. So that is vector B, which is now what? B minus, because that is now the negative of vector B. It's a free vector, remember, so you can always, displace the vector. But this time around, the vector is in exact opposite direction as its former vector as B. So that becomes, this now becomes the negative of vector B. We have talked about negative vectors already. So if we now want to add these two vectors using our triangle law of addition, what will we get? We get a vector from A to B. So this becomes vector A, this is minus B. So plus minus what? Vector B. So what we have there is vector A plus minus of vector B. And what is that? Vector A minus vector B. So subtracting two vectors simply means adding the negative of the second vector to the first vector. And that is how we subtract vectors, geometrically. The last thing we're going to look at is what we call multiplication of this vector by a scalar. Let K be a real number and A a vector. Then the product K times A is a vector in the direction of vector A and of length K times the length of vector A. Wow. Let us see what this means geometrically. So if I have a vector here, say vector A, okay? Now let's assume that I have another vector here, vector A again on it, another vector here, vector A. So this is vector A, still vector A. Good. What do we observe here? Now, if I, from this initial point to this terminal point, let me call here point O to point P. From point O to point P, let me assume it's just one vector, which I call vector B. What do we observe? We observe clearly here that vector B is what? Is 3 times of vector A. Okay? Because this is vector A, another vector A, another vector A. If I stretch it as one vector, I call it vector B. You observe that vector B is equal to what? 3 of vector A. So 3 of vector A makes up vector B. So what are we saying here? We are saying here that vector B here is simply a scalar multiple of vector A. Now if I multiply vector A 3 times, it gives me vector B. Okay, so I've multiplied vector A by a scalar 3. So this 3 here is what we are calling K. This 3 here is what we are calling what? K. We say 3 belongs to R, so this is K. So I multiply a vector A by what? 3. That gives us a vector B. First observation is that this vector B, which we have, obviously is in the same direction as vector A. So whatever direction vector A had, it will be the same direction as the scalar multiple of vector A, which is the new vector B. Second thing the second thing we should take note from here is this. Now, the length of this vector, this new vector B, from 0 to P, the length of vector B, okay, is equal to what? 3 times the length of vector A. So if vector A, for example, is 2, the length of vector B will now be 3 times 2. Okay, so vector A and vector B are in the same direction, but vector B is longer than vector A because vector B is 3 times of vector A. So vector A and B are in the same direction, but the length of vector B rather, is equal to what? 3 times the length of vector A. So in this case here, our scalar 3 is what? Is a positive what? Real number. We have other cases where it could be negative or 0. So let's see what happens. So again, we have our vector A here, but now we want to scale it up. But now vector A, we now have vector A this way, and then another vector A, and another what? Vector A. So we have a vector now from this point again to this point. Call this point again point O, and call here point P. Let's see, do we have the same observation here? Yes, we do. Our first vector was in this direction. The other vectors are now in the opposite direction. What is happening here? From point O to point P, what do we observe? We observe that from point O to point P, we still have 3 of vector A, right? Yes, we still have 3 of vector A. But what again do we observe? I say call this one vector B, no problem. What else do we observe? We observe that this time around, these other 3 vectors are in the opposite direction as the first vector, vector A. The vector A was like this, okay? Then these other vectors, A, the next 3 vectors are in the opposite direction as vector A. So it means that the other vectors are the negative of vector A. So I simply write minus 3 of vector A. So my vector B from 0 to P, vector B is equal to what? Negative 3 times what? Vector A. Why negative 3? Because this time around the vectors are in the opposite, the exact opposite direction as vector A. But do not forget, they are collinear vectors. That's why this is coming up. They are collinear vectors or parallel vectors, which I have discussed earlier. So the next question, what we should take note of here again is that vector B and vector A this time around act in exact opposite direction. Okay, where K 3 here was positive, vector B and vector A were in the same direction. But when the scalar here is negative, it tells you that vector B and vector A are acting in the opposite directions. What happens to the length? Now the length of vector B is equal to the modulus of minus 3 times the length of vector A. Please, these two things here are different. While this one means the length of vector A, this one here simply means the absolute value of the real number. Absolute value in the sense that a length can never be negative. Okay, so this absolute value sign takes care of any negative number that comes out of here, so that the absolute value of negative 3 is the same thing as what? 3. So technically we are B, the length of B is still 3 times the length of A. However, the negative sign initially tells us already that vector B, has been scaled in the opposite direction as our original vector, vector A. So we call this concept the scalar multiplication of a vector. And of course, if our K is 0, what does that simply mean? It means that the scaling is, so we have vector B would not be what? 0 times vector A. And what would that be? 0 vector. So no scaling has taken place there. Alright, so with the 0 vector. So K can be any value, positive value, can be negative. It can also be the 0, the number 0. In that case, B is just equal to 0, the 0 vector. So we'll stop here for the first video, and in our next video we shall look at other concepts, like the Cartesian coordinates, and then in that same next video we shall now translate this geometry. Beg your pardon. We shall now learn how to also represent vectors algebraically, apart from these geometrical representations, because in actual sense, in practice, what we use are actually the algebraic nature of vectors and not really the geometric nature. I hope you understand this first lesson. Please leave a like on this video and comment, and also do not fail to subscribe to my channel if you've not done so already. Thank you, and bye bye for now.